See, last class we started at the end to design the, we got the block diagram for the speed loop, and we started to design the controller based on the pole zero cancellation, and we found that pole zero cancellation will lead to instability here, because we are losing the S time. Let us start with that one, speed control. Now our reference, this is the omega S reference. Here is our PI controller, that is Kn into 1 plus Tns divided by Tns. Now this will give the current reference and the current transfer function, approximate current transfer function, which we can use in the speed loop is 1 plus 2 sigma S. The sigma we know, it is the sum of the smaller time constant. Okay, that is the converter lag and the current filter time constant. This will give to the machine. If you see, this is Ra by Km by Tms. This will give our speed feedback. This will come feedback. We have the gain as well as filter. Now, when we are considering the speed, the pole zero cancellation, okay, that is Tn. Let us see. Let us write the transfer function for this one. That is omega S of output feedback divided by reference is equal to Kn Ra by Tn K2 Km into 1 by S, 1 by 1 plus 2 sigma S to 1 by S into 1 plus Tns. This is from here, this one, divided by this, the this is the open loop gain, that is the from here to here, not the feedback loop, that is the GS part, plus 1 plus Kn Ra by Tn K2 Km into 1 plus S square into 1 plus 2 sigma S into 1 plus Tns into our feedback filter, that is K1 by 1 plus T1s. Now, if we use the pole zero cancellation, that means if we are cancelling this with this one, larger time constant, then our final transfer function will be of the form will be Kn Ra by Km K2 into 1 plus T1s divided by, after the cancellation, if you properly write down the transfer function, it will be S cube Tn Tm T1 plus S square Tn Tm plus constant Kn Ra K1 divided by Km K2. So, if you see here, the S time is missing, S square is there, S cube is there, S time constant is there. So, S time is missing in the characteristic equation, that is the denominator. Hence, the speed control system is unstable. So, the loop should be optimized using a different approach. But if you see, if you do not do the cancellation part and if you write down, the S time will be there, all the time will be there, that means system is stable. Now, the question is optimize it. Optimize means we have studied in the context of front end AC to DC converter. So, we will again repeat that one here for clarity. See, general consideration for optimization. For optimization, that means we are optimizing in terms of the bandwidth. See, the dynamic performance of a control system is good if the controlled variable very rapidly reaches the reference input. Ideally, for any frequency of input variation, that means if in the closed loop control system, the input we give ideally for any frequency of input variation, that means we give a signal with the sinusoidally varying, frequency varying, let the amplitude be constant. Then output should track the input variable instantaneously. That is what we want. What we want when we vary the input, here variation we are trying to do with various frequency of signal with constant amplitude. Then input should track the output should track the input. That means for different frequencies of operation, if the output tracks the input, that means the ratio between the output and the input will be 1. So, but as the frequency increases because of the system lag, slowly the system's response, that feedback signal will not be following the output. So, that way if that frequency and frequency component as the input frequency varies, the output gain will slowly decrease. So, there we talk about the bandwidth. So, for a practical system in terms of frequency range, the modulus of the output gain should be very close to 1 over a wide frequency range, that is bandwidth. That means the ratio between the output and the input. So, if you see here, we want something optimized. We choose our controller such that the gain, modulus of the gain should be 1 for as fast as possible, log omega here. Now, so optimization aims at bringing the modulus of the frequency characteristic as closest to 1 over a wide frequency range. This is also called modulus hugging. This we have studied when we were going through the controller design for the AC to DC converter. The same technique we can use here. So, what we want now, let us find out the transfer function. Without pole zero cancellation, let us write down the transfer function. If you say, so now without pole zero cancellation, the omega feedback yes divided by omega RS is equal to Kn Ri by K2 Km into 1 plus TNS because of our PI controller, and again because of our feedback time constant because of the filter. Then finally it will be S square Tm Tn into 1 plus 2 sigma s into 1 plus T1s plus Kn Ra K1 by K2 into Km into 1 plus Tns. Okay. So, here if you see here, if we expand this portion, if you expand this portion alone, let us do that one, that is 1 plus 2 sigma s into 1 plus T1s. Okay. Then this will be 1 plus 2 sigma s plus T1s plus s square T1 2 sigma. See, this also we can write as 1 plus s into 2 sigma plus T1 plus s square T1 2 sigma. See here, these are filter time constants T1 and 2 sigma, that is because from the current control loop. These are smaller time constant compared to our electromechanical time constant. So, because this loop is, this is coming in a loop where the maximum response depends on the electromechanical time constant. So, this also we can neglect this one, on practical purpose we can do it, and this approximately we can represent as a first order lag, again like a first order case, that is 1 plus delta s, where delta is equal to 2 sigma plus, that is delta is equal to 2 sigma plus T1. So, that means order of the denominator we can reduce it. So, still the characteristic equation is well within the frequency range of our system with which it responds. So, if you do that way, finally the transfer function we can write it like this. The whole purpose is to bring the whole system for modulus again, whether we have to bring it either to the second order or third order, because we know the how to do the optimization for second order as well as third order. So, let us see what is the order of the system if you do it here. So, the final system will be Kn Ra by K2 Km into 1 plus Tns into 1 plus T1s divided by s square Tm Tn into 1 plus 2 sigma s into 1 plus T1s plus Kn Ra K1 by K2 Km into 1 plus Tns. Now, this we have approximated as 1 plus delta s, where delta is equal to 2 sigma plus T1, this one. So, the final transfer function will be if you do the if you properly simplify this one, the final will be Kn Ra by Km K2 into 1 plus Tns into 1 plus T1s divided by S cube Tm Tn delta plus S square Tm Tn plus K0 K1 Tn into E. S time is there now plus K0 K1. So, the denominator, if you see here, it is a third order one. Now, this 1 plus Tn T1s and 1 plus into 1 plus this 0, this we can take care of like the current transfer transfer function by appropriately giving a delay to the reference input. Okay. So, the transfer function which has to be optimized for finally to be optimized for our closed loop control is this one. Because this 0, this we can eliminate the effect of this one by giving a filter. The input is filtered using this time constant, using these two first order filters. So, we can take care of this one. Now, let us take the denominator. Now, again let us go back to our optimization. If you see here, the optimization taken, we know it for the second order system. Let us go back to the previous one. For a third order system, the Fj omega, if it is B0 plus j omega E1 by A0 plus j omega A1 plus j omega square A2 plus j omega cube A3. So, one condition we set from the numerator, but here we are not worried about in our system numerator, because that we are taking care of by giving a filter to the input, same like our current controller. So, it is B0 is equal to A0, B1 is equal to A1. Then finally, if you take the mode Fj omega in our front end AC to DC controller, we got this equation A0 square omega square A1 square divided by A0 square plus omega square into A1 square minus 2A0 A2 omega raised to 4 into A2 square minus 2 A1 A3 plus omega raised to 6 A3 square. So, we will be using to make the modulus as close as possible to 1 for wide frequency range. We can eliminate this one. We can eliminate this one also using the condition A1 square is equal to 2A0 A2, A2 square is equal to 2A1 A3. Now, let us use this one for our compensation. So, let us write down this condition and our transfer function and then try to do the effect. The speed loop, this will be equal to omega Fs divided by omega Rs. Omega Rs we are passing through a filter. So, this will be 1 plus Tns into 1 by 1 plus T1s. Then the final transfer function will be Kn Ra by Km K2. Let us call this one as a constant K0 divided by S cube Tf Tn delta plus S square Tm Tn plus. So, this is K0, K0 K1 Tn plus K0 K1. Okay. Now, the condition for optimization we got. What are the condition? We will write it here. That is, one condition is A1 square is equal to 2A0 A2. Now, A2 square is equal to A1 A3. So, this shows from this one A1 square, which is A1. This is, oh, S time is missing here. There is an S time here. Yes, oh, sorry, there is an S time here. There is an S time here that we forgot, right? S time is here. So, A1 is the constant of the S time, that is K0 K1 Tn. So, if you see there, K0 square is equal to 2 K0 K1 Tm Tn, and A2 square, S square time, that is Tm Tn, that is Tm Tn square is equal to 2 K0 K1 Tn square Tm into delta. So, now from this one we can find out our Tn. That Tn we can substitute it here. Then from the K0 we can find out Kn. So, if you do it simplifying, Tn will be, we will get Tn is equal to 4 delta. Delta is equal to 4 into 2 sigma plus T1, and we know sigma is equal to converter time counts the current filter. So, this will be equal to 4 into 2 Tt plus 2 T2 plus T1. This is our Tn. Then, substituting this one, finally, our K will be Kn, that is our PI controller, Kn. P gain, Kn will be Tm Km K2 divided by 2 K1 Ra into delta. This will be the Kn. So, we got Kn optimization, we can get Tn. Now, let us substitute this one back to the equation and simplify it. The system will be the final hour omega. Okay, let us go to the next page. Final omega S feedback divided by omega S R will be of the form 1 by, that means this omega R is after filtering through 1 by our previous numerators. Numerator means 1 by Tns into 1 plus 2 filters of 1 by Tns into 1 plus T1s, or we can have another filter of 1 by 1 plus T1 plus Tn also is possible. Okay. Now, this will be finally of the form 1 plus 1 by 1 plus 4s delta plus 8s square delta square plus 8 s cube delta q. So, this one, what is the transient, this is the Laplace domain, what is the transient response of this one with a, for a unit step? We can find out the output for a unit step omega t will be of the form 1 minus, you can find out e raised to minus t by 2 delta minus 2 by root 3 e raised to minus t by 4 delta into sine root 3 by 4 delta into t. So, if you plot the response, see, let us take here t by delta as the x axis. So, this is our 100%. So, this will be approximately this is the 100%, this will come within 2% of our final value. 2% of the final value, that is the settling time, approximately 13.3 delta settling time, and our this will be approximately 7.6 delta, and we get an overshoot of approximately 8.7%. So, this is a good way of we have optimized the system. This is called the modulus Hugging. Okay. Now, there is another way of so also it is called symmetric optimization by computation. This is called, this type of optimization literature is called symmetric optimization by computation. Okay, we can write it here. Symmetric optimization by computation. So, this can be also using graphical methods, that also we will study, so that we can use these techniques appropriately whenever it is needed. Let us go to the next one, symmetric optimization by graphical methods. So, the previous transfer function, that is omega feedback S divided by omega Rs, we got it like this, that is 1 plus 4s delta t, 1 plus 4s delta t, that is 8 a square delta square plus 8 s cube delta cube. And previously, if you know, there we had this denominator here. The denominator was, what was the denominator? The denominator was, we will write it differently, that was the 1 plus Tn s into 1 plus T1s. And I told effect of this one we can remove by reference, we are the reference we are passing through this filter, that is, if you have the reference is here, we will pass through two filters of the form 1 by 1 plus Tns, 1 by 1 plus T1s. Okay. and Tn we got 4 delta. So, this also can be approximated with one time constant. Summation we can take it 1 by 1 plus Tn is equal to 4 delta plus T1 in this. So, that a filter of the time constant of 4 delta plus 1 omega r, we feed it and give it here. Okay. Then effect of this one, this will be cancelled and final transfer function will be like this, and we have how the response of for this one we have found out using the computational method. Now, we will talk about symmetric optimization by graphical method. See, if you see the closed loop controller, let us go back to the closed loop control system. See, you have the reference coming here. Okay. Reference, that is our reference. Then we have the controller, then the controller, our plant transfer function, okay. Then our feedback, it is coming here. So, what we want, let us find out the open loop gain. Open loop gain means we are removing this one. Okay, for ideal control, this feedback what is coming here, you should always track the reference. Okay. Also, since it is going to control and plant which has frequency dependent elements and reference also varying with the frequency. So, feedback signal you should not give any phase shift here, even if it is gain is same gain comes here, and if it gives a phase shift of minus 180 degree, negative feedback become positive feedback. So, the loop gain once it comes for unity gain, this phase difference should not be close to minus 180, should be far away from 180 degree. So, if we can do that also, that is also another optimization. So, let us take open loop gain. So, let us take our transfer function, go back to our transfer function, hold the transfer function and find out the open loop gain. Yes, let us write down the block diagram once again. That is gain into 1 plus TNS divided by TNS, then our current controller loop, that is 1 by K2 by 1 plus 2 sigma S. So, here 1 by K2 current reference, then finally RA by Km divided by TMS. Here is our omega S feedback. Then our filter. Filter is equal to K1 by 1 plus T1S. Okay. Now, to find out the loop gain, we are breaking here. So, let us find out when the signal comes here, what is the gain and what is the phase shift. So, phase shift, when it becomes phase shift for the unity gain, see, when it comes here, let us find out the loop gain and the phase shift here. Okay. So, when you do that one, let us draw the border plot first. Let us find out the loop gain first. Then from the loop gain, we will draw the block diagram. That is open loop gain. So open loop gain will be, that is F0 S is equal to Kn Ra K1 by Km K2 into 1 plus Tns divided by S square Tn Tm into 1 plus 2 sigma S into 1 plus T1s. Okay. So here also we can use the approximation. Delta is equal to 2 sigma plus T1, and this one KNRA Km by K2, this one let us call as K4. Okay. Then the final transfer function will be, that is open loop gain, F0 S will be equal to K4 into 1 plus Tns divided by S square Tn Tm into 1 plus delta S. This we are trying to find out another way of optimizing the loop by choosing Kn and Tn using the symmetric optimization using graphical methods. So this is the open loop gain. Now from the control system point of view, the system will be stable. This open loop gain at the unity gain crossover frequency, it goes up by minus 20 dB per decade, and at the gain crossover frequency, if we can have a sufficient phase margin, the system is stable. We can stabilize the system. So let us write down let us draw the border plot of this one. Again the loop gain. This will be equal to K4 divided by S square Tn Tm into 1 plus delta S. Okay. And numerator we have 1 plus Tns. Okay. Now if you see here, there is a 0 at Tn, there is a pole at delta S. Now we want 20 dB per decade. So if you F0 j omega, if you place Tn here, 1 by Tn, and 1 by delta with respect to 1 by delta. Okay. See, up to here it is minus 40 dB per decade because of the S square. Then the moment the 0 comes, it will shift to till it reaches here 20 dB per decade. Okay. Then again go minus 40 dB because of this effect. See here the effect of the pole will come. So here minus 40 dB per decade, this is minus 20 dB, this also minus 40 dB per decade. Okay. So we have to choose Tn such that. Now if you draw the phase margin, see minus 40 dB per decade. So up to this point, slowly it is minus pi. Then because of the effect of this one, it will slowly go. Again the effect of the 0 comes, and finally again it will go to minus dB. So we choose the Tn such that at this point we will have the maximum phase margin. This is called the phase margin. So, we should have the maximum phase margin. Okay? Phase margin at this gain crossover. Okay? Now, we have to design our Tn such that we have, it should cross the gain crossover frequency, this axis at minus 20 dB per decade, and you should get sufficient margin. So, this is in log scale. So, let us take, so usually we will design such that it will be the usual practice is to choose the crossover frequency omega c, that is omega c here, at the geometric mean of the two carrier frequency. That means, let us write down that one. Let us go to the next page. The usual practice is to choose the crossover frequency omega c, our omega c at the geometric mean of two corner frequency. This is omega c is we are playing to place at the geometric of the two corner frequencies, two corner frequencies. Okay. Now, from our previous example, the Tn we can approximately choose as that 1 by Tn. Tn is equal to 4 delta. We found we can use that one here itself also. Tn is equal to 4 delta. So, if we choose 1 by Tn is equal to 1 by 4 delta. So, we are already choosing this approximate. Usually, this 1 by Tn should be away from the 4 delta, 5 to 6, that margin. So, if you take this one, 1 by Tn is equal to approximately 1 by 4 delta, then let us find out using this one, let us find substitute this one in the loop gain, and let us find out what is the phase margin we are getting. Okay. And based on this one, at the gain crossover frequency there where the gain will be 1, let us find out what is Kn, and with that Kn let us find out what is the phase margin we are getting. So, if you are not getting the proper phase margin, again we will try to adjust this Tn with respect to delta, 1 by Tn with respect to 1 by delta. So, then we will see. So, this is a trial and error. So, since we have already got a Tn value from the previous thing, we will use that one and we will see whether we are getting the correct margin. This we will study in the next class.